Okay, so Maya, you can unmute and take over when just finish the bio here. So Maya Kopylova is a professor in the Department of Earth, Ocean, and Atmospheric Sciences at the University of British Columbia, where she has held a faculty position since 2000. Her research focuses on the composition and evolution of the Cratonic Mantle, as we'll hear about today, diamond and kimberlite geology. She has conducted research and fieldwork in Canada, Russia, and Southern Africa, and has worked extensively with industrial partners in diamond mining and exploration as well. So please welcome Maya and take over, please. Oh, you can unmute or,
You
oh,
can.
there we go.
That's
Okay.
fine. Yeah,
Okay.
yeah. I'm unmuted myself. Uh, Good morning, everyone. Um, I think I'm not a perfect fit for the topic of the seminar series because I don't do Archean crustal geology. Uh, I look at the Archean mantle. And until recently, we weren't able to date very well the processes in the Archean mantle. We knew the relative sequence of events in the mantle, but we were approximately at the same stage as the early geology when we didn't have the tools of absolute radiogenic related dating at our disposal. But relatively recently, maybe 20 years ago, we developed our methods of radiogenic dating to some extent that we know now the absolute ages of processes, and we can date them relatively accurately in the mantle. So we see that lots of processes are still active in the uh, Archean mantle while the crust is stable and do not show any signs of the um, interesting metasomatic happening in the mantle. So, and in this cartoon, we see the visual representation of those processes with different squiggly lines of different colors, so all fluids and metasomatic agents. So we'll discuss the connection between the crust and the mantle to make it more interesting to this crowd of people who mostly do their crustal geology. And recently we revisited our understanding and definition of what a craton is. So before we thought that that's the part of the crust and mantle with ages older than 2.5 billion years. Now we just switched from the crustal centered definition of the craton to geophysical centered definition of the craton. And now we define cratons as segments with thicker lithosphere, the lithosphere thicker than 150 kilometers, and something that has been stable for 1 billion years, so since the Proterozoic. And we also understand that cratons are a patchwork of different terrains with different ages of stabilization, but I will focus mainly on these terrains inside cratons that have Archean ages with respect to the crustal geology. And I will structure my talk today to tell you about three different time slices of the mantle processes, the initiation of the cratonic geology in the Archean, then Proterozoic modifications through different kinds of metasomatic processes, and then latest Phanerozoic modifications. And we see that many of those processes are not expressed in the crust. So the summary picture for my talk can be like the one to the right, where we have a lot of processes happenings down below in the mantle, but absolutely calm and non-active um, non-active environment in the crust. And the mantle for me is something very practical. I can touch it, I can cut, slice through the mantle, I can polish the mantle, I can study the mantle, and I get my mantle samples from kimberlite pipes. They can be full of different kinds of mantle material, different xenoliths with various lithologies and textures, different crystals, smaller crystals, macrocrysts, and larger crystals, megacrysts. And we study all of them, and that's the basis of my story today. I will start with Archean domains in the Cratonic Mantle, and Archean domains are mostly Herzbergites. So they are made mostly of olivine and Orthopyroxene with a little bit of accessory garnet, and the garnet would be a typical purple color, typical Herzbergitic garnet color. And how do we know that those Herzbergites are Archean? So let's first look at garnets. So this is the diagram we commonly use in diamond geology. We are plotting chromium against calcium oxide, and this diagram is convenient because it can give us metrics for depletion and pressure origin, the depth origin. So as we go to the left, we have more and more depletion, and as we go higher, we have higher pressure formation of garnet. So when we're looking at those black points on the background, we're looking at the compilation of garnet xenocryst found in the volcanics that erupted through the Archean crust. So these are Archean garnets, and you see the sizable proportion of these garnet is Herzbergitic. So the diagram is divided into Herzbergitic, more depleted garnets on the left, and lersolithic garnets, less depleted on the right. So these high degree of depletion showing by many of those Archean garnets is also confirmed by high degree of depletion we see in olivine composition. So here we're looking at the plot that shows the covariance of the rhenium osmium model ages and the olivine MG number. So you see in the Archean, our olivine is extremely depleted, giving us MG numbers between 91 and 93. So these are Herzbergitic olivines. And if we look at the histogram that is a compilation of worldwide ages for the Cratonic Mantle, then you see these mode in the Archean. So indeed, so some of those segments are Archean. And okay. But ideally, we should date the mantle not with rhenium osmium ages, because these are model ages that give us quite large errors of plus minus 100 million years, because they depend on many assumptions. So ideally, we should date the mantle with isochrones. But the isochron method of dating is very capricious. It requires a lot of material and it can be applied only to certain lithologies. But that method can give us really low errors if it is done properly. And I will be quoting several times this work published in Chemical Geology recently, and that work reported internal isochrons for garnet-rich mantle rocks, and age uncertainties is really small. That's absolutely brilliant to have less than 1 relative percent of uncertainty for these types of ages. So these are low dispersion internal isochrons, internal meaning that they are done for a single xenolith. And when we look at Archean isochrons for lutetium, hafnium geochronology, geochronometry, we see only a minor part of our cratonic samples give us Archean ages. Okay, so the a larger proportion of samples are more recent. And what are we dating when we getting Archean ages of the cratonic mantle? So we're getting the age of massive melt depletion. This is as much as 40% melt depletion and extraction. So at these degrees of melting, Clinopyroxene is fully exhausted, and we are moving all that melt up and creating continental crust with this melt. And we still don't know for sure what was the initial event that started that massive melting. So that is still controversial and debated. So some people would say that that's the ascent of the plume and high pressure melting. Some other model would say that that's shallow melting in the mantle wedge above the subduction zone. But we all agree that after that initial event of crustal continental crust generation, we develop cratons by continent collision. And let's now move to the Proterozoic mantle. And Proterozoic domains in the cratonic mantle is made of lithospheric. So you look at that sample and you see almost 10% of the sample is bright green chromium diopside. You also see garnet, and that garnet has different colors, so that's lithospheric garnet. And sometimes we see really interesting textures when Clinopyroxene rims garnet. And if we look at compilation for rhenium osmium ages for different cratons, we see almost half of these model rhenium depletion ages would be Proterozoic. So this would be our diagram, the histogram for the central slave craton. We can look at the similar data for the North Atlantic craton and see in the Proterozoic, almost half of our samples plot, and these ages of the rhenium depletion are quite younger than the ages of the crust formation that we can approximate with the zircon ages. So we see poor correlation between the crustal building events and what's happening in the mantle. And let's turn back to our garnets. So now we're looking at the Proterozoic garnets, and you see that these Proterozoic garnets now give us only the lithospheric trend. So all these Herzbergitic garnets disappeared, and this trend is called lithospheric because it's controlled by equilibration with Clinopyroxene. So Clinopyroxene also um, uh, has chromium and calcium in its composition. So this equilibration between garnet and clinopyroxene, that's what controls the trend. And again, these dots are the microcrystal and xenocrystal sampled by volcanics emplaced through the Proterozoic crust. And we also can deduce the degree of depletion based on the comparison of our data, empirical data, with the experimental data. So we're looking at these red and blue or black fields, and these are experimental residual garnets produced by 40% melt extraction, where clinopyroxene is completely exhausted, or 20% melt depletion when we still have clinopyroxene, and therefore we have lithospheric garnet. And when we can use one more line of evidence to say that Proterozoic mantle is lithospheric. So if we look at these summary diagram for diamond inclusions, we see that Herzbergitic diamond inclusions are Archean, so they plot with these rhenium osmium ages, and Proterozoic diamond inclusions are lithospheric. They plot between 0.7 and 2.1 billion years. And let's take out that lutetium hafnium isochron again. And now you see that most of our cratonic samples are actually Proterozoic. So, and they have these textures, so typically a lot of garnet and a lot of clinopyroxene. And we see the later origin of those domains rich in garnet and clinopyroxene also in our samples. So we commonly see veinlets made out of clinopyroxene in olivine rich mantle. Those veinlets can be garnet clinopyroxenites, then they can be zeolites, so that's very typical. And when we look in the thin section of these samples, we also see garnets with strange shapes like these, surrounded by clinopyroxene. And when we look even further, we see that clinopyroxene makes coronas not only around garnet, it also makes coronas around orthopyroxene. And these rims can be as thin as 10 microns, or they can thicken up to 0.5 millimeter. And sometimes we see the generation of those coronas in the very early stage. And we can imagine that originally it was the intercrystalline melt of fluid that migrated through grain boundaries and then entered into the reaction with orthopyroxene and deposited clinopyroxene around it. And interestingly, in samples where we see that addition of garnet and clinopyroxene, we also see quite a large sizes of grains. So olivines, clinopyroxenes can be as large as 2-3 centimeters. So indeed, we're looking at mantle pegmatites. And we think that these extremely coarse-grained textures were caused by fluid-assisted recrystallization with fast kinetics. So we can intuitively say that perhaps the addition of garnet and clinopyroxene was caused by the influx of calcium-rich fluids, because all the minerals that we're creating are calcic rich. But we can quantify it even better. And we did that for xenolith in Chidlak in North Atlantic craton, where we compared the initial composition of the mantle that we reconstruct based on mineral modes and mineral compositions with the resulting composition of xenolith that we simply analyzed by XRF, by grinding, powdering these xenolith. And the difference between the initial composition and the measured composition is approximated composition of the metasomatic agent. And so we see that quantitative summary of that metasomatic agent here. So all these elements that give us the positive numbers would be added to the mantle, and these elements would be subtracted from the mantle. So we see that 20% addition of calcium, the only major element with the unequivocal gain of the budget. We're also adding potassium. We're adding the entire budget of potassium and water because we are creating phlogopite that we commonly see added together with clinopyroxene. And we're adding these elements at the expense of sodium and a little bit of alumina and chromium. But because the major addition is in calcium, we can say that we are looking at carbonatitic metasomatic fluids. And at these pressures and temperatures, we are looking at approximately 200 kilometers. The metasomatic agent exists as supercritical fluid. So it's not melt, not gas, so it's something in between, high density fluid, very condensed solute or melt. So we can then use experiments on melt to compare what we see in our samples with the reaction products between the initial peridotite and different compositions of melt. And indeed, we see generation of clinopyroxene and garnet in those reaction zones if we react carbonatite with peridotite, or if we react silicic carbonatitic fluid with peridotite. Again, we are getting a lot of garnet and clinopyroxene added. And these reactions that would create these calcic silicates would be reactions of decarbonation. So the mobile fluid rich in carbonate would give away calcium to silicates and emits carbon dioxide. So the exsolution of carbon dioxide would make that fluid immobile. And that's why we have a different name to describe these reactions. They are called also the reactions of carbonation freezing. So, and these clinopyroxenes apparently are the byproducts of these calcium added to the mantle and carbon dioxide escaping from the mantle. And we can visualize this type of metasomatic reactions in this cartoon. So when we see carbonate-rich fluids, they penetrate through the mantle, making metasomatic channels rich in clinopyroxene and garnet. If these carbonated and very oxidized fluids by chance have a contact with the mantle, they can also go through a different type of reaction, so-called redox freezing. So, and that is the reaction when oxidized carbonate component would be confronting with the reduced mantle, and the carbon would be reduced and deposited as diamond. So let's look at the compilations of our lutetium hafnium isochron ages and compare what we see in the Proterozoic with the crustal events. So now we are comparing those bars of different color at 3 different cratons, slave, carp-wall, and Siberian craton, with something that is happening in the crust. So the first thing that I see is we have different events, different pulses of carbonatitic metasomatism. So for example, here, 2 different pulses on the slave craton. And on the slave, we have, and also in the carp wall, we have different crustal events like orogenic events, large igneous provinces, generation of large dike swarms, and only some of those metasomatic events would be visible in the crust. And we have also some other crustal events completely not represented in the mantle. So the link between the crust and the mantle is really poor or tentative. So let's dive now back into the mantle. So we now know how these clinopyroxene-rich veinlets formed, how these garnet veinlets formed, but they show transitions to autopyroxene-rich veins. And we can have Websterites, we can have autopyroxene garnet-rich domains, but mostly we're adding autopyroxene. However, these autopyroxenite veins and addition is restricted only to some of the cratons, not everywhere where we see carbonatitic metasomatism. And when I say we're adding autopyroxene, we're adding up to 40%, we're adding almost 15 extra volume percent of autopyroxene. So we're going from original 25% of autopyroxene in Herzbergites to almost 40% of autopyroxene, how it's seen in the carp-wall mantle. And guess what? The autopyroxene introduction also has been dated now. So if we look at this study for carp-wall samples, the authors divided all the samples into green and red. So for green samples, we see the hafnium depletion ages around 1 billion years. And these green samples show a lot of autopyroxene, up to 50% of autopyroxene. And other red samples with older depleted model ages around 3 billion years, they show a lower amount of autopyroxene. So the authors concluded that much of autopyroxene was introduced in the Proterozoic. And why that introduction of autopyroxene occurred? So most likely because of metasomatic with more silicic fluids, also fluids rich in halogens, mostly in fluorine, that were that originated from the subducted oceanic lithosphere, some lithologies like eclogites and carbonated pellites. So here we're looking at the study again of carp-wall xenolith, and we're comparing different lithologies of these xenolith. And these autopyroxene-rich garnet Herzbergite shows the highest amount of water and highest amount of fluorine. And we can also say that the amount of Orthopyroxene correlates with amount of fluorine here. Okay, we're finished with the Proterozoic mantle, and now let's look at the Phanerozoic domains in Cratonic mantle. They are quite different. So they have different textures. They have titanium-rich garnet compositions. And when we look at the summary diagrams for ages in the Cratonic mantle, only minor part of these mantle would be giving Phanerozoic ages, so maybe only 10% of those ages would be Phanerozoic. And if we just look at North Atlantic craton and the histogram of rhenium depletion ages there, again, only minor part would be Phanerozoic with ages. So, and in our lutetium hafnium isochrons, only those green samples would give us Phanerozoic ages, again, relatively minor part, but with really interesting textures. Let's look at compositions of Phanerozoic garnets. So you see that we have these low chromium garnets, lithospheric, but not quite, because even though they are in the lithospheric area here on that diagram, they are high titanium garnets. And we have the special name for these garnets, G10 in the diamond slang, so high titanium megacrystal garnets. So they are plotting in this pink field here. And these high titanium garnets exist in textures like these, in sheared peridotites, where we see a coexistence of large porphyroclastic grains with small neoblastic grains. And if you know your metamorphic petrology, you would immediately say that these textures are young. They are unequilibrated. Given enough time, especially at high temperatures of the mantle, these textures would re-equilibrate and make equigranular mosaic textures. But we don't see that type of annealing. So we know that these textures are young. And what else is young in these samples? The presence of contrast, geochemical contrast between porphyroclasts and neoblasts in all different in all different geochemical parameters. Also, we see quite a lot of zoning in porphyroclasts, so all these compositional contrast should be homogenized and erased as a result of long residence in the mantle, but this is not what we see happening. Also, we see thermal disequilibrium. So you see, these are pressure and temperature calculated for these type of sheared samples. And we see temperatures variation up to 400 degrees at a given pressure. So apparently these temperatures didn't have time to re-equilibrate on a steady state geotherm. So we looking at some consequences of a recent heating episode. And this metasomatism, because it adds titanium, is called titanium metasomatism, but it also brings a lot of other elements, calcium, aluminum, sodium, and iron. And this titanium metasomatism is especially water-rich. So we know these from different lines of evidence. So one of those lines of evidence is the presence of these tabular neoblasts. They are unlike isometric neoblasts with some stress recorded in them. These are strain-free neoblasts that formed as a result of annealing of larger strained porphyroclasts. And it's necessary to have some grain boundary fluid in order to anneal and recrystallize these porphyroclasts into tabular grains. And if we have water, we lower the effective viscosity of the mantle. So, and the mantle, you can imagine that mantle crumbling. So, and that mantle crumbling, deforming, and making strained samples, not because we increase the stress, but simply because we increase the amount of water in the mantle and make it crumble. So this process is called hydrous weakening. And we see evidence for this hydrous weakening in some of the cratons. And this is especially instructive when we can observe the mantle samples brought to the crust by two adjacent contemporaneous kimberlite pipes. And in one pipe, we would see a wetter olivine, then in another pipe, and then we see stronger deformation associated with these wetter olivine in the mantle. And titanium may be related to hydrogenation of the mantle because of these paired substitutions. So in order to keep hydrogen in olivine, it must be paired with titanium to make that substitution for magnesium and silica. Well, so let's look at the exact ages given by these deformed sheared samples. It's so good to have these lutetium hafnium isochrones because they can give us their accurate estimates of age that can also help us to say whether this texture development is exactly at the time of the kimberlite emplacement, or we can discern between the time of the kimberlite emplacement and this mantle process. And before, with rhenium model ages, we weren't able to do that. So now we can distinguish between these ages, and we can say that these textures and all these other events that we see happening relatively recently are shortly predating kimberlite emplacement. And the difference between the kimberlite emplacement and these processes is less than 150 million years. And before, we knew that the sheared fabric is young, but the estimates for the exact residence time of this fabric in the mantle ranged from 500,000 years to 50 million years. So now we know that it is more like 100 million years. So we can also think whether that's totally accidental that we have that hydrous titanium metasomatism very close to the time of kimberlite generation and emplacement. And I think that this is not accidental, and we're actually starting to create kimberlites with this inflow of proto-kimberlitic fluids rich in water and titanium. And we're now looking at the slice of this mantle with the fluids coming on the left. So that's the channel of the proto-kimberlitic fluid generation that generates iron and titanium-rich garnets and clinopyroxenes that we see as megacrysts. It in the areas more distal from the channels of travel for these fluids, we're also generating these sheared peridotite, and in both megacrysts and peridotite, we see a lot of shearing, so the presence of hydrous weakening process there. And later on, when we further react the fluid with the mantle, we make kimberlites, and they entrain those titanium-rich megacrysts and also titanium-rich olivines that we see as macrocrysts in kimberlite. And let's now summarize what's happening with compositions of garnets. So we move from Archean garnets to Proterozoic garnets to Phanerozoic high titanium garnets. And this evolution is the same as the evolution we see in a single grain of garnet very commonly. So in all cratons, in all lithologies, when we see zoning in garnet, that zoning is exactly like this. So we go from Herzbergitic core to litholitic calcium-rich rim, and then to titanium-rich rim at the very last stages. So I'm showing that evolution for 3 different studies, but I can find much more examples of this evolution. So is it why we seeing that evolution only going in one way? Again, is it representative of the entire cratonic mantle, or why we seeing only this temporal evolution? And my answer to this, that's not representative of the entire cratonic mantle. That's only what we see beneath kimberlite provinces. Yeah. So and what is happening away from kimberlite provinces, outside of the kimberlite provinces, we may never know. We don't have samples even to discuss what's happening in the mantle outside of kimberlite provinces. So in these segments of the mantle around kimberlites, sampled by kimberlites, we see how we progress from Archean Herzbergitic mantle to Proterozoic mantle, that evolution happening because of multiple pulses of carbonatitic metasomatism, producing a lot of garnet and Orthopyroxene, and then approximately 150 million years prior to the kimberlite birth, we're preconditioning the mantle to the birth of kimberlites by the change of metasomatism to hydrous titanium-rich fluid. And we are also softening the mantle so that it is deformed now, and then we make Phanerozoic kimberlites. And that brings me to conclusions. So we see that some of mantle processes are well expressed in crustal geology. This is the initial generation of the crust, but then we are going through the Proterozoic processes with lots of silicic and carbonatitic metasomatism. And carbonatitic metasomatism is more widespread. It's seen not only beneath continents, it's also seen beneath oceans, while silicic metasomatism is restricted only to some of the cratons. And that carbonatitic metasomatism forms calcic silicates, not carbonates. Carbonates do not stay in the continental mantle, so carbon dioxide escapes to the crust and melts. And then the final events of titanium-rich hydrous metasomatism preconditions the mantle to the birth of kimberlites, and this is what's happening beneath kimberlite provinces. And with this, I'll finish and welcome your questions.
Thank you so much, Maya. Just a reminder, you guys can ask question in the chat and I can read it out, or you can raise the hand and ask directly.
Oh, maybe I can start while our people come in with questions. So when you talk about depleted mantle, do you think you refer to just upper part of a mantle or to the whole mantle? What role do you think play in it that temperature of the mantle was high in Archean time and cooled over time? Could it sort of explain this change that you see?
Okay, let me find the appropriate diagram to discuss this. Yeah. So when I'm discussing the depleted mantle, I'm discussing only the mantle sampled by my kimberlite xenolith, and the deepest samples we have coming from depths of 250 kilometers. So below in the asthenosphere, we don't have empirical samples, so we know relatively, we don't know well what is happening in the asthenosphere. We don't have samples, we only have the results of modeling. And the results of modeling, I don't trust them very much if they are not confirmed by what I see in my samples. And you also asked about the models that say that in the Archean we would have higher temperatures. I don't see that. Yeah. So I see in my Archean samples, they would fall on these model geotherm 40 milliwatt per square meters. And the same thing I'm seeing in the younger samples. So in my mantle above 250 kilometers, I don't see that evolution from hotter samples to colder sample in more recent times. Yeah, so maybe what was different, the adiabatic temperatures in the asthenosphere, but not the geotherm temperatures in the empirical view.
So how do you explain this high depletion in Archean? What in your mind are responsible for it?
Okay, so maybe we should go to one of my first slides where we discussed these models. Continue to share. Yeah, so that is something that is still outstanding question for many of us, and you know lots of modeling and soul searching was done for to answer that question. So this extremely extensive melting, we don't know how that happened. So Griffin and Olbach will say that that would happen in the plume. So that's why it was almost 40% melt extraction, because it was really massive plume related melting. But Graham Pearson and some other authors would say that look at the samples that came from mantle wedges above subducting zone, and those samples would be the most depleted sample in the different terrestrial environments. So that's why if we want to explain the extreme depletion in craton, you have to look at these mantle wedge samples and ophiolites. Well, yeah, so, and I don't have my own opinion about the causes of this extreme melting in the Archean.
Okay, thanks. I have a couple more questions, but maybe I'll let other people go first and at the end come back.
Yeah, so we have one from Hua Huang, who is asking what processes transport titanium from subducted lithologies into the mantle source region?
Well, let's see. Let's see what type of fluids would be transporting titanium here. If we think that that would be a subduction, then we know that it has to be the supercritical fluid bringing us oxygen and hydrogen and carbon, because sometimes we see diamond generation when we have a lot of fluorine associated with these fluids. Yeah, I think that's the only type of idea that you can get. Um, I don't know what would be the complexation of titanium that would be especially transporting it. Yeah, I don't have an answer to that. Yeah, sorry.
Okay. There is another question from Ilya Windeman, who is asking, when is the oldest nodule? 3GA? Why are no older nodules in context of Earth evolution?
Yeah, interesting question. uh, I don't know. Ilya, can you answer it yourself? Yeah, do you have any ideas of your own? Can Ilya go in and unmute himself?
Yeah, he can.
Hi, everybody. Yeah, I've been thinking about it, but it's a pretty widely known fact that there are no oldest nodules. Like the oldest one is like in the Kapval craton. Somebody may correct me, and why is that? So continental roots are not being formed before, so we get different style of plate tectonics. So
okay, yeah. So now with your prompt, I can probably suggest something else. Well, we're if we want to find the oldest nodules, we we try to search the Kapval mantle, because there we have terrains up to 3.7 billion years old, but also look at the Greenland, and Greenland with even older crust segments would probably be even better than Kapval, but in this part of the crust we don't have any volcanic rocks that can bring us deep samples of the mantle to the surface. So I think that's the controlling parameters in the absence of extremely old nodules would be the paucity of samples together with the real rare crustal terrains with ages over 3 billion years.
Thanks. Maybe while other people come in with more questions, maybe I can ask one more. So I'm just curious if you have any explanation why you go to this carbonic metasomatism, and when in Phanerozoic you go to this hydrous metasomatism? Is it something to do with sort of subduction of carbonates, and carbonates kind of form this carbonic fluids, and in Phanerozoic at low temperature in a mantle, maybe it happen at deeper level, and so at that point you don't release carbonic fluids in a subduction, but it happens you release water in subduction. Do you have any thoughts on it?
Yeah, I would. Yeah, that's a very interesting question, and we've been pondering over that question since we discovered that carbonatitic metasomatism would be predating the titanium-rich metasomatism, and we think that that's more a question of really limited vision of us looking only at the kimberlite-related terrains. And it is not, I don't want to say that we cannot have titanium-rich fluids in the earlier time. So the thing is that if we're all having Phanerozoic kimberlites as the final point of our data collection. That's why we're looking at generation of titanium-rich fluids only in the Phanerozoic. Kimberlites also were erupting in the Proterozoic, and the only, but we don't have a lot of reference to Proterozoic kimberlites because most of them would be completely eroded. So kimberlites would be really surface related textures, something that we see in the upper 2 kilometers of the mantle of the crust. So with erosion, all those older kimberlites would be completely destroyed, eroded away. But I can recast all these ages instead with respect to the kimberlite emplacement. So I would say 100 million years before kimberlite emplacement, titanium-rich metasomatism, 2 billion years before kimberlite emplacement, carbonatitic metasomatism, rather than just giving you the absolute time frame, Phanerozoic and Proterozoic. Okay, and why we're seeing the change? I think that titanium-rich metasomatism is necessary to create kimberlites. So we may still have that carbonatitic metasomatism, but the amount of that titanium coming in and the amount of water coming in all of a sudden just overwhelms the relatively minor carbonatitic volume of metasomatism, and that's why all of a sudden it just seems more prominent.
So do you think it has to do with the fluids releasing from subducting plate sort of at different depths, or is it with diffusion, or how these fluids go through the mantle and to the crust? So, I guess I'm asking if you think about what process separates these types of metasomatism in time.
We don't have any data to create a good model about it. And I'm just really think that we should start with empirical data, and if we don't have empirical data, I don't like to just make esoteric models that cannot be tested. So can you maybe suggest a way how we can test your idea? that we all of a sudden we have more input of the subduction related fluids, and that's what creates that titanium rich metasomatism. How can we test that?
Well, it's very far from my expertise, so I'm just making it up. But I'm wondering if it has to do with release, sort of timing of release during subduction, or alternatively, I can see it maybe has to do with rate with which these fluids migrate through a wedge and into a crust. But I'm probably completely wrong.
Well, what I can say that several papers ascribed the origin of kimberlites and their emplacement to the movement of subduct plates under the ocean, and you can trace how the amount of kimberlitic eruptions would roll over following the influx of subducted related fluids. So I can quote several of those papers for you. And also the most recent paper by Jernan suggested that it's more about rifting than about the subduction. So you see the rollover of the asthenospheric mantle as a result of rifting, and you see how kimberlites are generated in response to some increased convection in the asthenosphere, and the asthenosphere coming closer and with fluids now penetrating the lithosphere. So not necessarily that's subduction, it can be also rifting. And again, if you want to have the exact reference to that paper by Jernan, I can then mail it to you, and maybe you can distribute it to the listeners.
Thank you.
Okay.
We have another question from Ryan Rehwinkel, who's asking, do we see evidence for the redox freezing reaction seen in your experiments in the Archean samples and/or other mental domains?
Yeah. Okay, so let's go to Archean. Okay, so asking about redox freezing. Yeah. Yes, we see the evidence for redox freezing in the production of those diamonds associated with typical metasomatized segments. So when we see these metasomatizing fluids bringing in additional calcium and additional incompatible elements, and also iron and alumina, we see minerals associated with diamond formation would be enriched in these elements brought by these metasomatic fluids. So yes, redox freezing is one of the processes we commonly see very well expressed in diamond formation.
Great. Do we have any other questions, or should we thank Maya? Okay, I guess can say thank you for the great talk.
Yeah, thank
Thank
you,
you.
Ian. Yeah, thank you, everyone. And thank you, Andrei, for inviting me.
Mhm.
And I'll just get out.
Thank you, Maya. And we will have a next week talk by Roger Fu from Harvard, talking about palemagnetic data from earliest Archean, and sort of continuing on this theme. So see you all next week.
Mhm. Okay,
Great.
thank you.
See you
Bye.
next
Thank
week.
you. Mhm.